Continuing intro to polar coordinates. Let me just do one other real quick polar coordinates on its own terms problem. Suppose you're given r and theta, and we just want to plot that. And the task is not necessarily to convert it to rectangular yet, although we can do that in a minute to check our answer. The task is to actually plot that point. Well, that's going to be a lot more helpful if we have these circles drawn, although you don't have to draw that, have to do that certainly. But it's going to be at radius 2.5, so it's going to be halfway between the 2 circle and the 3 circle. And, angle minus 7 pi over 4. Let's see. If you're going minus, it's 1, 2, 3, 4, 5, 6, 7. Aha. That's really coterminal to pi over 4. So this is really another equally accurate polar description. It's really 2.5 plus pi over 4. And it's going to be right in here. It's going to have that radius 2.5. And then if we wanted to get the x and y coordinates, x is just going to be 2.5 cosine pi over 4, which is going to be 2.5 times root 2 over 2. And y is going to be 2.5 sine pi over 4, which is 2.5 also times root 2 over 2. Okay, and we can get the decimals for that, but that's not super important. So that's another kind of thing we can do. Mainly, I'm interested in polar coordinates on its own terms. One thing that I might show in another video is you can actually buy, or even better, print out on the web polar graph paper with circles. It looks like this with circles, and then it has strategically placed radial lines, and it makes it easy to graph polar coordinates and think of polar coordinates without having to convert back and forth. But I am also interested in converting. And in the other video, I showed how going from r and theta to x and y is pretty easy. It's just r cosine theta, r sine theta. That combination shows up in many, many, many places, and this is one of them. Well, what about if we know x and y, and we want r and theta? It's mainly not bad. Oops. That's mainly not too hard, but there is one significant subtlety. So let's draw a picture again. Oops. Okay. Here's our point. And we know this distance, r. We know this side and this side. And we want to get this side, and we want to get the angle. Okay. So I want you to think about that. R equals, what does R equal for a minute? And I claim that it's not super hard to see what tool we need to figure that out. If I'm given these two sides, suppose this is like 3 and this is 2, how are we going to get that third side? And of course the answer is Pythagoras. R squared is x squared plus y squared. And I hope this video is working because it's really lagging behind here. The computer's slow. Or in other words, r is the square root of x squared plus y squared. So that is Pythagoras right there. So let me put that in the pretty printing over here. We have r equals the square root of x squared plus y squared. It's so much nicer in some contexts to not have that square root that I'm going to go ahead and just write down the version without, without the square root. But if in terms of a one-stage formula to get r, it's going to be the square root of x squared plus y squared. So that's something we can get some practice in. What about theta? Okay. So we'd like to get something that just says theta equals. But that's not quite going to work. Okay. So let's see. Let's switch to blue for theta. Theta, well, this is exactly the kind of problem we were just doing when we were introducing inverse trig. And this is why I did inverse trig before polar, because you really need it at this stage. We know that theta fits in here. Remember, the known quantities are x and y. Suppose this is 3 and this is 2. Can I get theta? Well, let's see. I don't want to have to use r. Even though I can get it out of here, I want it all to relate back to x and y. And the trig ratio appropriate to x and y is tangent. Oh, okay. So we actually do know the tangent of theta. and that's equal to y over x. Okay, so that in itself is a really good thing to write down, even though it is not solved yet for theta. Okay, and that really almost is the right place to stop. It's very tempting to say, okay, I know how to solve those guys. That's the inverse tangent. I just know to use the inverse tangent button on the calculator. Is it true that theta is the inverse tangent of y over x? Well, not quite. Not quite. Let me give you two examples here. I'm going to erase and restart the picture. Two quick examples. Don't want to make it too long. Let's say we're at a very simple point. Let's say that's 4 and that's 4. Okay, so xy is 4, 4. And so r, let's just do r real quick. R is going to be the square root of 16 plus 16, which is, if you simplify it, it's 4 root 2. Now, it's true that tan theta, it's definitely true that tan theta is 4 over 4 equals 1. Let's see, is it true that theta, I'm losing space here, is that inverse tan of 1? Yeah. The mystery angle whose tangent is 1, oh, that's pi over 4. Yeah, and it totally looks right. That's pi over 4, 45 degrees. Okay, so it checks out there. So sometimes it totally does work. But here's one where it's not going to work. I'm just going to go exactly opposite. Minus 4, minus 4. Okay, so here I want this theta. Okay, it's still totally true that tan theta is y over x, because it's basically just sine over cosine, height over horizontal. Those kinds of formulas never screw up in any quadrant. But the inverse tangent stuff, we know inverse functions are weird about quadrants. And so the thing is, if you put in, yeah, the problem is this is still minus 4 over minus 4. That's still 1. So if you put in inverse tangent of 1 into the calculator, it doesn't know that it came from minus over minus and not plus over plus. That's still going to give you pi over 4. It's going to think it's in this quadrant. By definition, inverse tangent only ever gives you something in these two quadrants. Okay, and so it's not going to give us the right answer, which is 5 pi over 4, which is pi plus pi over 4. I know it's getting really ugly and messy here. Okay, so this is not always true. The answer is not too hard to get out of it, though. The thing is, all we had to do is add a pi. It's going to give us, instead of this one pointing here, it's going to think it's on this line. Because remember, the tangent only cares about the slope of the line. And the inverse tangent tells you what's the mystery angle that would give that line. It tells us the simplest angle that gives us the slope of that line. Okay, so the upshot is that this is true if theta, if the point, let's say, is in Q1 or Q4. But the annoying thing, and this is just going to trip you up, guarantee it, unless you're really on your game and paying attention, you have to add pi if the point is in Q2 or Q3. Sorry about that. It's annoying. There's no way around it. The world is just like that. And so that's kind of annoying. And this is a really ugly thing to write, whereas this is not so ugly to write. But what's lurking there is if you actually want to solve for theta, you often do have to do this. Basically, the punchline is pay attention to quadrants. Don't write down an answer that's clearly wrong and just is in a completely wrong place. Roughly plot your point, and if the theta that you're giving me is in the totally wrong quadrant, probably what you forgot to do is add pi. It's not like it's hard to fix. Not like it's a big calculation, but you will often need to fix it. Okay, we'll get some practice with this soon.